So now let's talk about the chemical properties of the acids and acid derivatives. So when we talk about the chemical properties, we need to talk about the interconversion of acid derivatives. That means how can we convert one of the acid derivatives to another. So the type of reaction that controls this interconversion is called the acyl substitution reaction. So nucleophile acyl substitution, we have our acid derivatives, which have the R and C, the carbonyl group, C double bond O, and then we have Y. Y here refers to a leaving group. This could be a chloride if it's acid chloride, it's carboxylate if it's anhydride, it's alkoxy group if we are talking about esters and so on. And we have the nucleophile. So the reaction proceeds via the attack of the nucleophile to the carbonyl carbon because it's partially positive because of the presence of the oxygen. So now the oxygen will take the electrons of the double bond, and the oxygen will have a negative charge. So this is the first step, and a tetrahedral intermediate is formed with an oxygen with a negative charge, Y, and we have the nucleophile. Y here, as we said, is a leaving group. So the Y will leave while the double bond between the oxygen and carbon will regenerate. So we end up with a different carboxylic acid derivative. So we started with the one that has Y and we ended up with the one that has the nucleophile. So what controls this kind of reaction and which group will act as a leaving group and which one will be the nucleophile? This is controlled by the reactivity of the different acid derivatives. So the reactivity of the acid derivatives goes down from acid chloride until the carboxylate or the carboxylic acid. So the acid chlorides are the most reactive acid derivative, followed by the anhydride, then the ester, amide, and then carboxylate. This is controlled by the basicity of the leaving group or of that group, which is the leaving group. So based on the basicity of the leaving group, the less basic group means it's more stable, means it can easily be created or it can easily exist in the reaction mixture. That means it will be a better leaving group. So the chloride is the most stable, is the least chloride with a negative charge, is the most stable, is the least basic. This is followed by the carboxylate group for the anhydride, and then for the alkoxy, for the ester, then the NH with a negative charge for the amide, and finally for the hydrogen with a positive charge here for and then for the carboxylate it's the hydrogen. So the carboxylate is the least reactive. Now we know that acid chloride is the most reactive. That means the chloride is the best leaving group. So we can substitute it with any other nucleophile from this list. So let's have um, a general look about how we can do this. So a general rule is that more reactive derivatives can be converted to less reactive derivatives. So we know that the acid chloride is the most reactive. So it can be converted to any of the other acid derivatives. So the acid chloride can be converted into carboxylate or carboxylic acid. This is by reaction with water or hydrolysis, so it can easily give you carboxylate. And we talked before about how the acid chloride are very, very reactive, and we should avoid as much as possible to have water with acid chloride because it will react very quickly with water to give you the carboxylic acid. Also, we can convert acid chloride to anhydride or to ester or to amide. The second one in the acidity, in reactivity is the anhydride. So we cannot convert anhydride directly to acid chloride, but we can convert anhydrides to esters, amide, or carboxylate. You can convert esters to amides or carboxylate, and finally you can convert amides to carboxylate or carboxylic acid. So how can we then synthesize or prepare the acid chloride since it's the most reactive acid derivative? We can do that directly from the carboxylic acid, but not via the nucleophile acyl substitution, but through reaction with thionyl chloride. So let's have a look on the acid chloride preparation. So when you have an acid like this one, which is benzoic acid, and you reacted with cyanide chloride in presence of a base like pyridine. So pyridine here act as a base. And we're going to see in the reaction mechanism how this base is important in this reaction. So this is pyridine. You're going to end up with the acid chloride, which is benzoyl chloride, and sulfur dioxide and hydrogen chloride. So let's have a look at the reaction mechanism. So the reaction starts here with the presence of, because the sulfur on thionyl chloride has a partial positive charge because of it's attached to an oxygen, and the oxygen is more electronegative than sulfur. It has more tendency to attract the electrons towards itself, or to take the electron of the lone pair, the electrons of the double bond. So the sulfur now will have a positive charge, and the double bond of the carbonyl group will then attack this sulfur. The presence of the lone pair of electron of the OH group of the carboxylate group then can also help in this reaction by creating a double bond with the carbon, creating a positive charge on the oxygen. So this is the first intermediate that is formed here. Well, the double bond between the sulfur and oxygen is broken, and a new bond is formed between the oxygen of the carbonyl group and the sulfur of the thionyl chloride. The second step now is that the double bond between the sulfur and oxygen is recreated. Oxygen in itself is not a good leaving group, but chloride is a good leaving group. So the second step is that the double bond between the oxygen and sulfur is recreated here, and then the chloride, one of the chlorides on the thionyl chloride, will leave as a leaving group. We still have the double bond here between the carbon and the oxygen of the OH of the carboxylate group with an oxygen that has a positive charge. We know very well that oxygen does not like to have a positive charge. It always likes to attract electron. Here comes the role of the pyridine or of the base that will relieve the oxygen from the positive charge. So it will take the hydrogen from the oxygen, leaving the oxygen without a charge, and the pyridine as a base will take this hydrogen. Now we have this second intermediate has been formed, and then the pyridine as a base, we said, will take the hydrogen from the OH. Then the third step now is the formation of the acid chloride. So for the formation of the acid chloride, we have the carbonyl group here in this intermediate. Again, the oxygen had the tendency to attract the electron. So the chloride that has been uh, that left in the previous step here, the chloride with a negative charge as a nucleophile will attack the carbon of the carbonyl group, while the double bond between the carbon and oxygen is broken. This is assisted by the presence of the carbon double bond oxygen. Once this has been done, now we have this intermediate. This intermediate has the oxygen with a negative charge. So this oxygen, because it took the electrons of the double bond, now the oxygen has a negative charge. This compound is not stable. It wants to relieve itself from having any charge. It wants to be completely uncharged because this is the most stable form of any compound. So what happened now that we look for the other leaving group that can easily leave, relieving the oxygen from carrying a charge. So what will happen is that the chloride will leave as a good leaving group, and sulfur dioxide will be created as a double bond will be created between this oxygen and the sulfur. So this bond is broken, and the oxygen, the negative charge on the oxygen will then make a double bond between the carbon and the oxygen. The end product will be the acid chloride, hydrogen chloride. The hydrogen chloride comes from this chloride atom ion that will leave as a good leaving group with the hydrogen that has been taken before by the pyridine and the sulfur dioxide. So this is the simple mechanism of how thionyl chloride react with an acid to form the acid chloride. So for again, let's go back to the acyl substitution reactions we talked about and how we can do the interconversion conversion between the different acid derivatives. So starting off with how to change or convert an acid chloride to anhydride. So to convert an acid chloride to anhydride, you need to do a reaction between acid chloride and an acid. So reaction between an acid chloride and an acid will give you acid anhydride. The reaction is the same mechanism we talked about for the acyl substitution. So the first step is the nucleophile, which is going to be this oxygen, is going to be our nucleophile, will attack the carbonyl carbon, which is partially positive, and this will create the, and of course the oxygen will take the electron, attract the electron of the double bond that will create a tetrahedral intermediate now, with an oxygen of the acid or of the nucleophile has a positive charge and still have the chloride and the oxygen, the other oxygen of the carbonyl group that has the negative charge. So now the second step of this reaction is the leaving group, which is the chloride here, is going to leave. We know that chloride is a better leaving group than the carboxylate. So the carboxylate itself is not going to leave. This is the nucleophile that will stay, and chloride is the better leaving group, so it's going to leave. So the chloride will leave, and also this hydrogen on the oxygen will leave, and the oxygen with the negative charge will regenerate the double bond of the carbonyl group. So we end up with an anhydride and hydrogen chloride. The hydrogen chloride comes from this hydrogen and the chloride that left as a leaving group. How to convert an acid chloride to an ester? Still the same mechanism, but now instead of using an acid, we're going to use an alcohol. So the alcohol now is going to be our nucleophile. So the alcohol as a nucleophile with the lone pair of electron plus the acid chloride. So you should know now what to do. So the first step is the attack of nucleophile to the carbonyl carbon, and this double bond will break. That will give us the tetrahedral intermediate. So O with a negative charge, the carbonyl oxygen and the chloride, and then the nucleophile. The oxygen now will have a positive charge, and then the R of the acid chloride. To give us the final product, now the chloride will leave as a good leaving group, and the oxygen and the hydrogen will be subtracted, and that will create, relieve the oxygen from its positive charge. The hydrogen will be subtracted, and the double bond will be recreated between the carbonyl oxygen and carbon. So we end up with the ester and hydrogen chloride now. Chloride is a better leaving group, so this is why it's leaving in this reaction. Acid chloride to amides, the exact same thing, but now we're going to use an amine instead of using an alcohol or a carboxylic acid in the first step. So the exact same mechanism. For if you want to synthesize or prepare primary amide, then you're gonna use ammonia. For secondary amide, you're gonna use primary amine. For tertiary amides, you're gonna use secondary amine. So let's have an example for how to prepare tertiary amide. So the reaction between a secondary amine when the nitrogen has two R groups, and the acid chloride, the exact same mechanism. The lone pair of the nitrogen will attack the carbon of the carbonyl group, and this will create the tetrahedral intermediate again. Oxygen with a negative charge, chloride, nitrogen that has two R groups, and the hydrogen, and it will now carry a positive charge, and this is the R of the acid chloride. The final step, we all know that chloride is going to leave as a leaving group. The oxygen will again regenerate the double bond, and this hydrogen is going to leave as a proton, relieving the nitrogen from its positive charge. So we end up with a tertiary amide and amine salt, because there are extra amines in the reaction mixture, so it will act as a base and it will react with the hydrogen chloride to give you a salt, because we know from last lecture that amines are bases and they react with acids to give amine salt. So what about tertiary amines? Will they form amides with the acid chloride? When you think about it, you think that the final step in the reaction is that the hydrogen from the nitrogen or from amine or from the nucleophile will leave to leave a positive to relieve the nitrogen or the oxygen or whatever the nucleophile is from its positive charge. So we need to have some hydrogen attached to the nucleophile. In this case, if in case of tertiary amine, so tertiary amine is a nitrogen that has three R groups. There is no proton here, there is no hydrogen, so the reaction will not proceed. Now let's move on to the second one, which is the anhydride. So we know that anhydride can be prepared from the acid chloride by reaction between acid chloride to reaction between acid chloride and acids. Now, the anhydride, it's the second one in the reactivity after the acid chloride, and the anhydride can be converted to the other acid derivatives. So anhydride can be converted to ester. How would we do this? It's exact same mechanism, but now the leaving group is going to be a carboxylate group, and the nucleophile is going to be an alcohol, because the carboxylate is a better leaving group. It's less basic, so it's a better leaving group, and the alcohol is better as a nucleophile. So alcohols will again attack in this case, if you have two different R groups, you can end up with two different products, because actually the alcohol can attack any of the two carbonyl groups. So we are now going to assume that both the R groups are the same. So we have the same anhydride, and then the lone pair of electrons on the alcohol is going to act as the nucleophile. It's going to attack one of the carbonyl groups, and then the carboxylate will leave as a leaving group. And then in the same way, the oxygen will regenerate the double bond, and the proton will be subtracted from the carboxylate anion that has been generated. So there will be the end product will be an acid and an ester. An application of that is the synthesis of aspirin. So during your practicals, you will have one of your practicals is to synthesize aspirin in the lab. And you will be provided with salicylic acid and acetic anhydride to prepare the aspirin. So aspirin is called acetyl salicylic acid. The structure of it is basically salicylic acid and an ester and an ester functional group, acetyl group. So salicylic acid is structure of salicylic acid. It has a carboxylic acid group and it has an OH, alcoholic or phenolic group. When an OH is attached to an aromatic moiety or to aromatic derivative, it's called phenolic. It's not called alcoholic. So, but it has similar properties like the alcohol. Now we have the alcohol, our alcohol, which is the nucleophile, and then we use acetic anhydride. So acetic anhydride is simply two acetic acids together with after removal of the water. So the lone pair of electron on the OH of the alcohol is going to be our nucleophile. So it's going to attack one of these carbonyl group and the reaction will proceed in the same way to give you the product which is aspirin or acetyl salicylic acid. So the acetyl salicylic acid here has a carboxylic acid functionality and it has an ester functionality. Remember that this ester or the alcohol here, the alcoholic group here, will not react directly under these conditions with the acid to give you an ester, but it will react with the anhydride to give you the ester. So this is why in your lab you will be provided with acetic anhydride and salicylic acid and will be asked to prepare aspirin. The mechanism of the reaction is exactly the same, so but you have to replace these R groups with salicylic acid or for the alcohol or with the acetic anhydride in case, so it's going to be CH3 in case of acetic anhydride. In the same way, we can also interconvert the anhydride to amides. Again, we can use ammonia. It will give us primary amide. If we use primary amide, that will give us secondary amides. If we use primary amine, it will give us secondary amides. If we use secondary amines, it will give us tertiary amides. The tertiary amines themselves will not react. So we either use ammonia, primary or secondary amine to give us the primary, secondary or tertiary amide. The exact same mechanism again, the attack of the nucleophile, which is the amine, on the carbonyl carbon to give us the tetrahedral intermediate. The double bond will be regenerated between the oxygen and carbon, and then the carboxylate is going to leave here as the leaving group, and the hydrogen will be taken as a proton from the nitrogen, and then the amide will be prepared. The third one in the reactivity series for the acid derivatives is the ester. So following the anhydride, the ester is the third most reactive. So the ester can only be converted either to amide or to a carboxylic acid. So ester to amide, the exact same mechanism again, but instead of having the carboxylate or the chloride as a leaving group, we're going to have the alkoxy group or methoxy or ethoxy depending on which alkoxy group as the leaving group. So the first step again, the attack of the double bond of the nitrogen, the attack of the lone pair on the nitrogen, which acts as the nucleophile, attack on the carbonyl carbon, making the tetrahedral intermediates, and then the leaving group, which is the alkoxy group, is going to leave, and then the double bond regenerated, and the proton will be abstracted from the nitrogen. So how can we then prepare the acids? We said that all the acid derivatives are more reactive than the acids themselves, and they can be converted to acids. So the simple way of doing this is to use water, in this case, as a nucleophile. So any acid derivative, if we use water as a nucleophile, the reaction will proceed in the exact same mechanism, and it will give us the acids. But depending on the reactivity of the acid derivative, the reaction will proceed either quickly or it will take time or it might need a lot of heat and acids as well. or a catalyst. So for the acid chloride reaction with water at 20 degrees at room temperature, the reaction will be very, very fast, will give you the acid and hydrogen halide. For the anhydride, the reaction with water, the reaction can proceed at 20 degrees at room temperature, but it will be a bit slower compared to the acid chloride, but it will take place at room temperature as well. This is because the anhydride is less reactive than the acid chloride. With ester, the reaction at room temperature will be very slow. We would need catalyst and we would need heat in order to give the acid and the alcohol. Finally, the amide, which is the least reactive. With water, the reaction is exceedingly slow and it will need catalyst and prolonged heating. So it doesn't proceed smoothly with water, but it needs a lot of time and needs a lot of use of the catalyst that will regenerate the acid and the amine, depending on which amine we use to prepare the amide. So for if you started off with tertiary amide, you're going to end up with a secondary amine. If you started off with secondary amide, you're going to end up with primary amine. And then there is the amide itself and the ammonia. So this now we now come to the end of our topics about the carbonyl compounds and their reaction. We talked about the carbonyl functional group, carbonyl compounds, which refers to aldehydes and ketones, and then the acid, carboxylic acids and their derivatives. We talked about naming, we talked about how to the different physical properties of them, and finally how to interconvert between all of these acid derivatives.